Here it comes. Okay, so welcome back to the online Graphs and Matroids seminar. We're happy to have our first speaker of the restarted session, Johannes Carmesin from the University of Birmingham. So take it away, Johannes.
Yeah, welcome everyone. And I just want to say it always was kind of one of the few highlights during COVID, kind of having this seminar to look forward to, and kind of I think it's great that's starting all over again. Yes, so I would like to talk, right? So Whitney proved that a graph is planar if and only if the dual matrix is graphic. And I would like to talk about how does this work in 3 dimensions. Okay, so let me start with a small introduction. Probably kind of some of you know this already, but just trying to kind of start from the basics, right? So just take a graph, embed in the plane, for example, the black graph, and then you can always draw the dual graph of the embedding, here indicated in red. And how do you do that? Put a vertex into each face, and if 2 faces share an edge, put an edge in the dual graph. And throughout the talk, I'm assuming that the graph and the dual graph have the same edge set, so I'm suppressing a bijection between the edges. And now Whitney asked the following crazy question: would it be possible to construct this red graph directly from the black graph? And of course, the answer is no, because the black graph may not have a unique embedding, and then there may be potential non-unique dual graphs for the respective embeddings. But we as matroid theorists nowadays know that the answer is almost yes, in that you can construct from the black graph a matroid, and which then turns out to be the cycle matroid of the red graph, right? So just to remind everyone, so the dual matroid of a graph is given by the bonds of the graph, so the minimal non-empty cuts of the graph, so they form the circuits of a matroid, which we call the dual matroid of a graph. And I denote that by M star of G. And then Whitney proved that a graph is planar if and only if its dual matroid is graphic. That means it's a cycle matroid of some graph. And this theorem of Whitney does not only answer the questions about the existence of the embedding, but it also tells us what possible embeddings there are. So let me explain that a bit. And so for this we need one definition. So that's so now embeddings a priori are a topological object, and we would now like to have a combinatorial understanding of what an embedding is. And so for this we need the rotator at a vertex. So just kind of you take a vertex and you just take the cyclic ordering of the incident edges in the embedding. So that's the rotator at a vertex, and the rotation system is just a rotator at each vertex. And then simple fact is that if you have 2 plane embeddings of a connected graph with the same rotation systems, then these 2 embeddings are topologically isomorphic. So this completely topologizes the problem, and we just have a combinatorial problem. We're interested in some graphs together with some rotators. And then nice consequence of this is that if you have 2 plane embeddings and they have the same 2 connected dual graph now, then these graphs these 2 embeddings are isomorphic. So why is this? Because if I have a 2 connected graph embedded in the plane, then all the phase boundaries are really cycles and not something more crazy. And then if I take a vertex of the primal, then all the edges going out in the dual graph, they would form a phase boundary, which by 2 connectedness would be a cycle. So they would uniquely determine the rotator. All right, so 2 connected dual graph uniquely determines the rotators of the embedding, and thus uniquely determines the embedding. Okay, so now we could use this to understand. Use Whitney's theorem not just to understand the existence of embedding, but really how all the embeddings look like. All right, so now you have a 2 connected graph G. And then the statement is, now you take an arbitrary graph H, so that the cycle matrix of G is the dual of the cycle matrix of H. And then kind of simple consequence of Whitney's theorem is that G and H have a simultaneous plane embedding. So you can embed both of them together in the plane simultaneously. And now, this tells you how all the possible embeddings of G look like. Why? Because you know that if you take an embedding of G, you could construct the dual graph H, and this must have the property that the dual of the cycle matrix of G is equal to the cycle matrix of H. And then there are kind of various graphs that represent the cycle matroid, and these are all the possible choices, and then bijection with all the possible embeddings. So that's kind of one reason why I think we should all like Whitney's theorem a lot, because it doesn't just tell us about the existence of embeddings, but it tells us what all the possible embeddings look like. And now what I'd like to talk about today is how could we do something similar in 3-space? Okay, so what's the embedding problem in 3-space? So now, I mean, we go from the plane 2 dimensions, 1 dimension higher to 3 dimensions. So we should also increase the dimension of the objects we would like to embed. So now we no longer have graphs, which are 1-dimensional simplicial complexes, but we have now 2-dimensional simplicial complexes. So these are just graphs, and then you have a set of triangles and you glue some 2-dimensional faces on it. So for example, on the left-hand side, you've seen a 2-complex, which is called the cone over K4. So you start with the graph K4, and then you do this topological cone construction. So this, you add an additional vertex to the 2-complex, and for every vertex of K4, you put in an edge from that vertex to this newly added vertex, and for every edge of K4, you add a triangular face to that new vertex. Right, so that's the cone over K4. And now we would, right, and the problem is you're just abstractly given a simplicial complex, and now you would kind of move the faces around a bit to get some embedding in 3-space so that the faces do not cross. And you can see that on the right-hand side that this is possible. If you take this red face and just move it, just bend it a little bit, then you have no intersecting faces. All right, so that's the embedding problem. So you're given an abstract simplicial complex, 2-dimensional, and you would like to embed it in 3-space. And there are various notions of embeddability: piecewise linear embeddability, topologically embeddability, differentiable embeddability, but people prove fast they're all the same. So we have one notion of embeddability. And yeah, so this is actually a problem that happens a lot in kind of the 2-dimensional space we work in. If you think about some skyscrapers, for example, we could give them the structure of a simplicial complex just by making the ceilings and the walls and some cells of the 2-complex. I mean, perhaps you more think about them as 4 cycles, but then just introduce some edge, splitting them apart, putting the 4 cycle into 2-3 cycles. So that's kind of not a big deal here somehow, and I will kind of do it quite often in the talk, that if there's a face and it has some boundary which is larger than 3, then just triangulate it and then put in some other faces. And then perhaps kind of more physical example is if you just take a pot of water, boil the pot of water, then you see some foam emerging there, and you see kind of a nice 2-complex coming up. Okay, and here comes my favorite example. Right, so these are all 2-complexes which you can embed in 3-space. And here's my favorite example of a 2-complex which you cannot embed in 3-space. So how do you construct this? So you start with the octahedron with 8 triangular faces. And now, right, okay, so that's in black the octahedron, and you put in all the 8 triangular faces, and then it looks like a round sphere. And now you add 3 more faces to it. One orthogonal to the x-axis, and which we here see in turquoise, and one in shaded green, which kind of is orthogonal to the y-axis, and a gray one, which is orthogonal to the z-axis. And actually, if you stuff in so many faces, you can actually prove this no longer embeds in 3-space. Somehow there's kind of too much stuff in there. Okay, so now let's yeah, so here's now an here's now an interesting fact about kind of how matroids come into play. Right, so let's start with an arbitrary 2-complex embedded in 3-space. for example, just kind of this black two complex I drew there with these 8 boxes stapled onto each other, right? So that's a nice 2 complex, and the faces would just be the 4 cycles of these boxes. And if we remove this 2 complex from the indicated embedding in 3 space, this leaves 9 components. 8 of them are the insides of these boxes, and then there's kind of the big outside region. And we refer to these components as the chambers of the embedding. And if we have a 2 complex embedded in 3 space, then we can, like for a planar graph, construct a dual graph of the embedding. So how do we do this? So we put a vertex into each chamber, and if 2 of these chambers, if they share face, we join these 2 chambers by an edge, right? So you can see that on the right, you can see the red graph, and this is the dual graph of the embedding we have indicated of the black 2 complex. Right, so you have kind of 8 vertices for these boxes, and then 1 outside vertex for the outside chamber. Right, and okay, so I mean, what would be very wonderful, but unfortunately isn't true, is that it would be very nice if we could compute the red graph just from the 2 complex C. But it can't be possible because the 2 complex C could have non-isomorphic embeddings in 3 space, which would then lead to non-isomorphic dual graphs. But I mean, we're Matroid theorists, we kind of know how it works in the plane, right? So you shouldn't even try to construct the dual graph from the 2 complex itself. But what you try for is kind of construct the cycle matroid of the red graph, right? So now we want to build from the black 2 complex some matroid that is equal to the cycle matroid of the red graph. And actually, you can do that. So let me tell you how you do that. So first, what you need is a matrix. So you take the edge face incidence matrix of the 2 complex. So that's a very simple object. Right, so I have to tell you, if I take an edge and I take a face, what's the value for this pair? So if the edge is not in the face boundary, then you just take the value 0. And now for each edge, we pick one direction. And for each face, we take a cyclic ordering on its boundary. And now if the edge is directed clockwise in that orientation, we put a +1. If it's directed anti-clockwise, put a -1. Right, so this defines your matrix with entries 0 and +/-1, which just encodes the incidences between edges and faces. Right, and now once you have a matroid, right, and now you pick your favorite field K, perhaps F2, F3, whatever you like. And now this matrix then defines your matroid. Right, how do you do that? So the ground set of the matroid will be the set of faces of the 2 complex, which then will be the edges of the red graph. Right, so the ground set are the faces of the 2 complex. And then every edge of the 2 complex gives you a vector, which is the incident vector of that edge, telling you how this edge is incident with some faces. And now you take the set of all those vectors, they generate your vector space. And now you take the matroid that is represented by that vector space. So whose circuit space is equal to that vector space. So that's just an analogy, right? Okay, so in this matroid I denote by M sub K of I. And the exciting fact is that this matroid is equal to the cycle matroid of the red graph.
Can I interrupt you just with a trivial question? Are the rows corresponding to the edges in the incidence matrix?
Yeah, I think everyone gets, I don't know, I on purpose didn't say that. So they're the elements of the matroid, which are the faces. And then they're kind of, you have one vector for every edge. And I think some do it kind of always take the transpose of the matrix. And
Well, I'm asking what you're doing.
You're saying I'm always taking the transpose because I'm getting confused. Yes, could be.
So your columns correspond to the faces. Is that a good way to think of it? So then the columns correspond to the matroid elements.
Okay, so if the columns correspond to the matroid elements, right, which are the faces, then the rows correspond to the edges.
Okay, so when you take the edge vectors and you take the space span, it's the row space of the matrix in that interpretation.
Yes.
Okay, thank you. That just clears things up for me. Thank you.
Yes, I think that's a very key construction. So thank you very much for the question. Yes, so so this is, I think, a very familiar construction for you, because I mean, if you think about in the plane, right? So there you could take the vertex edge incidence matrix of a graph, and then in the same way generate the row space from that matrix, and you're just going to get the bond matroid of the graph, right? So there's just the analog construction, but one dimension higher. And yeah, so the fact I want to show you is that actually, like in the plane, this matroid describes the cycle matroid of the red graph. Okay, so let's see why this is true. So we have to prove two things. So the first thing we have to see is that if we take an edge of the black 2 complex and take its incidence vector, that's actually a closed walk in the red graph. So why is that true? I mean, you have that edge over here, and then you have some faces glued to that edge. And these faces, they would be red edges in the dual graph. And then you follow them along and you get a closed trail in the dual graph, which goes once around that edge, right? So the instance vector of every edge, that's a closed walk in the red graph. And now we also need to show the inverse, right? So that if we take a closed walk in the red graph, that this actually is also in this circuit space for the black matroid. And there's a nice topological trick how to do that. So we take the red dual graph, and now we just established that for every black edge we have a closed walk. Its incident faces, they form a closed walk in the red graph, and now we just glue a disk on that. So for every edge of the black graph, we now glue a disk on the red graph, and this upgrades the red graph from a graph to a 2 complex. And actually this 2 complex now has a simultaneous embedding with the black 2 complex into 3 space, right? I mean, we know already that the red graph is the dual graph, and now for every edge of the black graph, we're going to add a face, right? So if we just look back at the embedding of the black graph, into each chamber we put a red vertex. Into each black face, we have like a red edge going across. And then when we have a black edge, we have a red face going through it like this. And now we have this nice simultaneous embedding of the black 2 complex and its dual red 2 complex. And then some simple topological computation gives you that actually this simultaneous embedding gives you that the red 2 complex is simply connected always. And then this means that all these phase boundaries we had, they generate all the cycles in the red graph. But this was precisely what we wanted to prove, right? That these incidence vectors of the edges, they generate all the cycles in the red graph. Yes, and this is the proof why this matroid MKI is equal to the cycle matroid of the red graph. And the key ingredient here was that you could upgrade this dual graph to a dual 2 complex and then show that it's simply connected, and this gives you this equality. And yeah, so and probably at this point you're very convinced that this matroid MKI is a very natural object, and I'd like to call it the dual matroid of the 2 complex C, in analogy to the dual matroid of graph. Okay, so now 2 complexes have dual matroids, so it's very natural to ask, do we get a Whitney theorem? And probably the first thing you would like to try is just like for graphs, right? A 2 complex embeds in R3 if and only if this dual matroid is planar. Sorry, it's graphic. Right, so just like Whitney's theorem. Yeah, but unfortunately, this is not true. And the first thing is, I mean, I was a bit sloppy here kind of in formulating it. I mean, just on the last slide, I made the definition of the dual matroid. It implicitly depended on a field K, and now I just left it out, right? So we have to be very careful how with the dependence on the field K. And the second thing is that this statement is simply not true, no matter what field you take. And here's a counterexample. And the counterexample is the cone over K5. So how does this work? So you start with the graph K5, and now we take this cone over construction. I think we saw the cone over K4 already, right? So it's the same construction. Take the graph K5, and then just take this one-dimensional cone, add one vertex, additional vertex for every vertex of K5, add an edge to that new vertex for every edge of K5, add a triangular face. And the claim is that this two right. So if you compute the dual matroid for this two complex, it's just a bunch of loops. I mean, if you write on the matrix, that's what you're going to get. But this two complex, and just trust me on this. But unfortunately, this cone over K5 doesn't embed in 3 space. And the reason why it doesn't embed is kind of the same reason why K5 does not embed into the plane. It's just kind of everything blown up by one dimension. And there's a very nice way to actually see that. And that's if you look at the top, if you take the cone over K5 and look at the top vertex, and then at this vertex, you can look, I mean, suppose there was an embedding, then you could take a small ball around that vertex, and then each edge going to that vertex would intersect that ball in a point. Every face going through that vertex would intersect that ball in an edge. So you would have drawn K5 on the sphere, which you can't. And actually, this graph I just geometrically described, you can just read off from the two complex directly. It's the incidence graph between the edges and the faces going to that vertex. Right, so and that's called the link graph at the vertex. And we come back later to this. But there's an abstract way to say it without referring to the embedding. Okay, so there's this counterexample, and just says this problem, this Whitney theorem in this kind of very naive way is not true. And then there's a last point, and that is, I mean, matroids are very nice because they don't care about if you have a bunch of edges in which order they appear on a cycle. And so that means that matroids just, topologically speaking, they just work on the level of homology, but they don't see some more complicated homotopical structure, which is very good because matroids are then much simpler than all these crazy things coming up where it's just kind of on these, all these crazy things with fundamental groups that don't show up. But for us, for this problem, it's kind of not so good because there are some crazy 3 manifolds which look on the level of homology, they just look the same, but you have kind of to look at these more complicated fundamental groups. And of course, our matroids have no chance to distinguish these two things, and they don't have then a chance to distinguish embeddability in the 3-sphere or some more complicated Poincare spheres. Okay, so but that's kind of a complicated topological problem, and we have a fairly simple answer to this, so don't worry too much about it. But yeah, there's some, right, so there's 3 reasons why we have a problem. So let's kind of see how we can solve this. Okay, so let's come back to this cone over K5. So what's really the problem there? Why is it making some trouble? And right, so right, okay, so if we have a planar graph and we take a vertex and we have all the edges going out, then we would expect that usually they would form a cycle in the dual graph of the embedding. But this is not always true. If you have a cut vertex, then the edges going out of that cut vertex, they wouldn't form a cycle in the dual graph, right? There would also be a cut vertex in the dual graph, etc. Right? So, and that's kind of very nasty thing, but it happens. And for planar graphs, it doesn't make any problems at all. Everything works nicely. But the same nastiness now can happen in 3 dimensions, but now suddenly it makes a lot of problems. And that's actually the reason why kind of this cone over K5 construction is a problem, right? I mean, okay, so assume we had like a very nice two complex embedded in 3 space. Think about like these boxes stapled on top of each other, which we had before. Then would be true that locally at each vertex, if you take the link graph, and I mean, which would be a planar graph because it would be embedded in that ball. And if you took the dual of that, this would actually be equal to the matroid restricted to the corresponding faces. I mean, just think about geometrically, right? I mean, you have kind of these nice boxes embedded, and then you take a vertex, take a small ball around it, and how the two complex intersects is that the link graph, now take the dual of this planar graph, and that's precisely how the matroid chambers are arranged, right? And this is right. So this is this definition of locality, which I kind of put there, the formal definition in the first line. So that looks a bit crazy. Perhaps don't think about it. I mean, think about it perhaps a little bit, except that there's a formula how you can abstractly compute it. But I mean, don't kind of try to understand it too much in this talk. So I think rather I'd like you to have kind of look at the blacks, at the gray thing at the bottom of this page, which just says locality intuitively means that the matroid sees all the link graphs. So it has all the information about the link graphs at each vertex, which you just get by restricting to all those faces that see the vertex. And then you can compute the link graph somehow from that. And this is obvious. This is what went wrong in the cone over K5, right? So the dual matroid was just a bunch of loops, so it carried no information whatsoever about the link graph at the top of the cone, which was a K5. And so the only way around it, I believe, is just to kind of forbid this strange behavior, to exclude these crazy embeddings, and just say we require that all the two complexes we consider are local. Okay, so this solves one of the problems, and the other two problems can be solved much simpler. So first there was this dependence on the field, and let's just be explicit about it and impose it, say something as weak as possible about the field, right? We just take an arbitrary field and want that this problem works for every field. And then there's this thing about the Poincaré spheres, and this problem magically goes away if you just assume that the two complexes are simply connected. So if every closed trail in the two complex can be generated from phase boundaries. And I mean, we have to put some condition, and I think it's kind of very natural to put in this condition. Okay, so now the new problem is, so you have a field K, an arbitrary field K, and you have a simply connected two complex that is local, and the hope is that this now embeds in R3 if and only if this dual matroid is graphic. So yeah, so kind of, yeah, so I mean, given all these counterexamples, probably they're kind of the most natural Whitney theorem we could aim for. And actually, that's true. So this is just kind of the problem kind of stated around as a theorem. So you fix your favorite field K, and now you have a local simply connected two complex. It embeds in 3 space if and only if the dual matroid is graphic. So how I'd like you to think about this theorem is kind of the figure below. So you start with your favorite two complex. Perhaps it is the octahedron with kind of 2 faces added in the middle. Then you compute the dual matroid over your favorite field K. And then if it's not graphic, then you can't be embeddable. So it's better going to give you a graph. So you see kind of in the middle, you see that black graph. And now you kind of feed that black graph to your two complex. And this graph then tells you how you should embed this matroid into 3-dimensional space. And that's kind of the last figure. And a nice bonus from this theorem is, I mean, we start with a two complex, and now we pick our favorite field to check this criterion. But once we've done that, we see that it does no longer depend on the field. So once we are embeddable, for every field, these two matroids, these dual matroids, we compute isomorphic. So if we're non-embeddable, the reason could be that kind of there are some crazy matroids, and here it's embeddable, and here it's not embeddable. I mean, then okay, so if the dual matroids are not isomorphic for different fields, then it must be that the two complex is not embeddable. But if the two complex is embeddable, then magically all these matroids are the same, and we could have done our computations over our favorite field. Okay, so the dependence on the field is as nice as you could hope for. Okay, so that's a theorem. So let me first talk a little bit about the proof. And like for these, now what the first thing we'd have to understand is, before with the planar embeddings, we had the rotators, the rotation systems, and now we do something similar in 3 dimensions. That's so what's the rotation framework? So that's the following. So you have a 2 complex, and at each vertex you have these link graphs, and they of course have to be planar, right? Because if you were embedded in 3 space, actually this would induce plane embeddings of all of these link graphs, and they have to be compatible in the following sense. So if you take one edge of the 2 complex, then this edge is a vertex in the link graph on the left and a link graph on the right, and all its incident faces, they would be edges sitting at that vertex. And then you would need that the rotator here on the left and the rotator on the right, they are either the same or one is the reverse of each other, because they actually come from the same cyclic rotation of the faces on that edge. Right? Perhaps a bit strange to think about it, but I mean, trust me, that's the condition. So you want a planar graph sitting at each vertex together with some compatibility on the edges. And there are kind of 2 ways they could be compatible. Either they are, the rotators are the same, then we color the edge red, or they're inverse of each other, then we color the edge green. And somehow the green edge is kind of, the green thing is better, the red thing is worse. So we need to have the additional condition that along each cycle, you are going to have an even number of red edges. So if all edges are green, it's super nice, but you need on every cycle an even number of red edges. And then Skopenkov proved in 1994 that a 2 complex has an embedding in some 3 manifold if and only if it has one of these combinatorial objects, so which we call an even rotation framework. Right, so this again de-topologizes the whole problem. All we have to do is, we are given a 2 complex, we have now to construct these plane embeddings at all the link graphs together with some compatibility. Okay, so let's, yeah, and don't worry too much about these details of the planar rotation systems and so on, about these rotation frameworks. I mean, I'll tell you when it gets important. Okay, so now I would want to give you a quick overview about how to prove this Whitney theorem in 3 dimensions. So first, what you'd have to do is reduce the whole problem to the locally 2 connected case. So to the case where all these link graphs are really 2 connected. And then you have to do another reduction step to reduce it so that all these link graphs actually have minimum degree 3. And there's kind of, yeah, some standard techniques to that. Okay, so yeah, okay, so that's already a little bit of work, but I mean, once we have on these very nice settings, kind of ideas get much more easier to explain and much more natural. Okay, so then the first memo we need to prove is that if the dual matrix is graphic and we have the locality condition and all the link graphs are 2 connected, then there exists one of these rotation frameworks, but it's not even yet. And then the second step would be to show that if you are simply connected, you have this minimum degree 3 condition, then actually this rotation framework is even. And for a very long time, I was kind of very confused at this step, because, and the reason is the following. So if you work, for example, over the field F3, then you don't need 2 lemmas, you just need 1 lemma. So you can directly construct this even rotation framework, and you don't need this assumption of simply connectedness. But this really was a red herring, because there are some fields where actually you can't go all the way to an even rotation system, but you have to have the step in between. So different fields work different. I mean, it's probably quite technical part of the proof, but I got quite confused about it. Okay, so once you have the even rotation framework, then you can use this lemma of Skopenkov to actually show that your two complex embeds in some three manifold, and then use Perelman theorem. So Perelman proved the Poincaré conjecture, which says that if you have a simply connected compact three manifold, then actually it must be simply connected compact two manifold, it must be isomorphic to the three sphere. Yeah, so that's kind of very, very rough overview of the proof. And just kind of to see kind of if you look at the proof strategy, kind of that's probably something we are quite familiar with kind of from graph minor theory. You have a problem. First, you reduce it to the highly connected case. And then kind of the situation is kind of much neater. Lots of kind of these crazy, yeah, these kind of non-uniqueness things go away. So you can kind of much more nicely argue in the highly connected case and have kind of easier structural lemmas. Okay, so now we have the overview, so let's kind of relax a bit and enjoy a few corollaries. So there's this theorem of Tat, which says that the matrix is graphic if and only if it doesn't have one of 5 excluded minors. And now we could use that, feed that into our theorem and see what we're going to get. So first, if you work with F3 representability, then it's very nice because you just get 3 excluded minors. Because F7 and F7 star, they already appear as excluded minors for F3 representability. So the dual matroid, if you build it up over F3, it never ever can have these minors. And then if someone comes and actually promises you that the dual matroid you construct actually is regular, then you just have 2 excluded minors. And probably most useful because, right, so now I think probably the most natural thing is to work over the field F2, because then you don't, when you compute the dual matroid, you don't have to worry about directions of edges, orientations on faces. It just always goes away. It's just kind of 0, 1 incidence matrix. And you actually can do that, and then you just get 4 excluded minors. Again, I mean, before I had like some weaker versions of the theorem, but yes, this is new. I couldn't do that before by F2. And that's kind of one of the fields that makes a lot of trouble. Yes, okay, so now let's kind of look a little bit deeper into the proof. So we have this lemma that if the dual matrix is graphic, then there exists this rotation framework. So let's understand how we can do that. And this is really kind of how you build the embedding combinatorically. So first, you know, the dual matrix graphic. So someone has to come and give us a graph so that the dual matroid is equal to the cycle matroid of that graph. And then we use can use locality to actually see that all the link graphs are already planar. Why? Because we know by locality that these link graphs are equal to this dual matroid restricted to these faces. So we know that these the dual matroids of the link graphs are actually graphic, right? And then by the 2-dimensional Whitney theorem, we actually get that they are planar because the dual matroids are graphic. All right, so the link graphs are planar from this notion of locality. But this doesn't quite give us a rotation framework because we need these planar embeddings at the link graphs to be compatible. And then, right, so G sub V is this graph which you get by taking the cycle matrix of G and just restricting it to all the faces incident with the vertex G, V. And because we were locally 2 connected, or the link graphs were 2 connected, their dual matroids are also 2 connected. So these graphs G sub V are 2 connected. And now you know that because these graphs are 2 connected, actually every face of these graphs G sub V which have dual planar embeddings with the link graphs L sub V, they will be bounded by cycle, and a cycle has only 2 rotation systems, kind of clockwise and anti-clockwise. And so at the 2 link graphs, because in the 2 link graphs at either end of an edge, they come from the same graph G, which gives dual graphs, you would have that, you would have the same cycle actually, which then would give you a theta at either end. And because the cycle only has the 2 rotation systems, the other would be the same. or they would disagree. So you're going to get a rotation framework. Okay, so that's kind of a bit more kind of this topological construct of this construction of the embedding, how it works. And now that we have a Whitney theorem, we could easily deduce a McLean theorem from this. So how does this work? So if you tell a topologist that you look at the cycles of a two complex, they would ask you, which cycles do you mean? Do you mean like the cycles of the one skeleton, which are just the cycles of the graph as we know it? Or do you mean the two cycles, which would be some faces, so that if you sum them all up, their boundary vanishes? For example, a two-dimensional sphere or torus or something like this. And actually, these two cycles, they also form a matroid. And this matroid is the dual matroid of the dual matroid of a two complex, which I would like to call the cycle matroid of a two complex. And these these two cycles of a two complex, they also form a vector space. Yes, so I mean these faces that form a two cycle, there's some vectors, and they generate your vector space. And now you say that a family of vectors is sparse if in every coordinate either all but exactly two of them takes the value 0, and one takes +1 and one takes -1, or all of them take the coordinate the value 0. Right, so that's kind of just like you know it from McLean's theorem in the plane. That's the definition of sparseness. And then this three-dimensional McLean theorem is that a simply connected local two complex has an embedding in 3 space if and only if its space of 2 cycles has a k-sparse generating set. So yeah, so that's like McLean in the plane. You're embeddable if and only if the sparse generating family. And there, yeah, in recent years, there has been kind of a lot of things happening in kind of this development of a minor theory in 3 dimensions. And one thing I'd like to point out here is a brand new theorem of Aggelos Georgopoulos with his PhD student, George Contagiaggio. And I think that's quite exciting. So what do they prove? So, I mean, right, okay, so if you have a graph, if you have a group, then associated to this, you have a Cayley graph, right? Kind of whose vertices are the elements of the group and edges are given by some generating set of the group. And similarly, you have a Cayley complex for that group where you take the Cayley graph and add some faces given by the generators. So this, for every group, you do not just get a Cayley graph, but a 2-dimensional object. And they proved that a group acts topologically very nicely on the 3-dimensional sphere if and only if its Cayley complex has an embedding in that in 3 sphere. And they're kind of similar theorems already in 2 dimensions. So this really kind of gives kind of a new perspective on this embeddability, so that you can have kind of these very nice embeddings. And I think very exciting technique that they developed in that paper is kind of a 3-dimension analog of this Babai lemma, which kind of very roughly right. So for graphs, the Babai lemma says you're given a graph and you have some group that acts on that graph, then actually you can kind of find very nice, you can partition the vertex set in some nice connected sets that are invariant on the groups, and then you can contract them all simultaneously, so that in the quotient you're going to get from this, the group acts transitively on that graph. Yes, and yeah, so I think there's kind of, in this area as a whole, there are kind of much more open problems than things have been answered. So what I talked about today is a bit of this connection between 2 complexes and regular matroids, but I think there's kind of much more to discover than we know. Very famous problem in the area is polynomial knot recognition. So very simple thing, you take the laces from your shoes, kind of somehow tangle them up in 3 space and glue the 2 ends, and now you try in polynomial time to kind of just make it to a round circle. And then you can also take your favorite theorem from graph minor theory and think about kind of what happens, how can we extend it to 3-dimensional space. So let me finish kind of was a very concrete question. So perhaps, yes, I think something every one of you knows is Hewitt theorem, right? You have a plane triangulation, and now you would like to 3-vertex color it, and you can do it if and only if all the vertices have even degree. And now this you can also do in 3-dimensional space. So in 3-dimensional space, you no longer want to color the vertices, but instead you want to color the edges. And because if you have an edge coloring, then it would induce a vertex coloring on all the link graphs. So this is then like simultaneously vertex coloring all the link graphs. And then the condition is you are 3 edge colorable. If an edge coloring means now 2 edges should get different colors if they're in a common face, and you're 3 edge colorable if and only if all edges are incident with an even number of faces. Sorry about this. I hope you can still hear me. So say if you can't. Yes, so the reason why I kind of like this theorem a lot is that in the proof, we actually use these dual matroids to construct the dual graph and then use them to show actually this dual graph is bipartite, which then kind of helps us to construct this coloring. Yes, and the open question is, can you do something similar in dimensions higher than 3? And this is kind of a very simple problem, and it's just kind of can be stated just in terms of graph coloring, right? So you see a triangulation of R to the D, and now you are interested in the vertex coloring of its one skeleton, right? Just the underlying graph, just the vertices and the edges. And it says that you can color it with D+1 colors if and only if every D-2 phase is incident with an even number of D-1 phases. And if you plug in D equal to 2, just gives you Hewitt theorem. If you plug in D equal to 3, then you can check that it's equivalent to what we proved. But yeah, I think high dimensions, I think it's a very exciting question. And if you think about it, it really should be true, because locally, just because you have these R to the D simplicities, right? You need the D+1 colors, and then there's kind of always a unique way how you can kind of continue it. So really, it should be true, like in Hewitt theorem, right? But yeah, yeah, it's open, and I think yeah, that's how I want to finish. Thank you very much.
Okay, so maybe we can unmute on the count of 3 and give Johannes a round of applause. So 3, 2, 1. Okay, are there any questions?
Yeah, I was wondering if there was any hope of pushing your theorem into higher dimensions, but if you restrict the kinds of embeddings you're looking at. So, I mean, obviously there'll be serious topological issues for higher dimensions, but if you look at if you sort of say, I'm only interested in certain kinds of ways to embed things to avoid things like Poincare in higher dimensions.
And we could still assume simply connectedness. I don't know whether it's enough. Okay, so I think, I mean, the problem somehow is, I mean, for our embedding to work, we needed that all these link graphs, they are they are planar, right? And we have like good control how to do that. And then in higher dimensions, you would actually need that they would be 3 spheres. I don't know. I mean, you have to get your head around, and perhaps you could at the right place get good conditions, but I think it seems like a harder problem, I would say. Because I mean, we don't completely understand when a 2 complex is isomorphic to, I mean, embeds in the 3 sphere, right? We need this assumption of simply connectedness. But yeah, perhaps you have a way around it. I think it's a very exciting question, and I don't know the answer.
Yeah, so I mean, it might eventually start to depend on the kind of embedding you do, right? I mean, like if the Jordan curve theorem wasn't true, we'd have 2 kinds of planarity. Maybe things start to go wrong, but you can sort of fix a simple combinatorial version that works.
Yes, I mean, definitely in higher dimensions, eventually piecewise linear is no longer the same as topological. But yeah, I mean, perhaps for one of the notions, you might have a chance.
Yeah.
Any other questions?
Yeah, I wanted to ask, there's this notion of locally 2 or 3 connected, looking at the link graph. And I don't have clear examples of how this compares with being too local. Like, I'm wondering if you can say an explicit example. I know that you can't really draw one here, but
Wait, so too local, you mean local over the field F2?
yep.
I think that's kind of just, I think it's two different conditions. I mean, that the link graphs are two connected just means you compute these link graphs and they're two connected graphs, right? And if they're not, then you could. Yes, so I think that perhaps it's not so easy to see connection, because if you look over the cone of K5, right? So then at the top, the link graph is K5, which is 3 connected, but it's not local over any field you work over.
Are the other link graphs not just stars? Sorry, maybe I'm confused.
Yes. Ah, wait, okay, wait, what do you, okay, so perhaps I didn't understand the question. So the question is?
An example of a locally 3 connected two-dimensional simplicial complex that isn't too local. Just because it's hard for me to picture such a thing.
Yeah, right. Okay. Okay, so I think I need to think about this.
Yeah, actually, could you go back to this remark that you had mentioned earlier about an example of something that is always local?
So sorry, what's the second question?
I was wondering if you could scroll back in the slides, this remark you had about an example which is always local.
Yes. It's very. No, I think. Wait, wasn't it that? Yeah.
Right. Yeah, it's like this.
Yeah, probably you need to add some junk at these other vertices, right? Yeah. So.
Okay. Yeah, sorry. I mean, I'm just asking to try and get a better feel for it. I understand what the definitions are, but I don't know of,
Yeah, I mean, I would
examples for
expect
this.
that if you start with a cone of a K5 and then you have kind of all these vertices of K5 where you aren't local, and you would try to add some junk there to actually make it local. But I think out of the top of my head,
Gotcha.
I can't tell you
Okay.
how, but I think it should be possible.
Okay. Yeah, no, thank you. That's helpful though. Thanks.
Any other questions?
I'm actually also interested to know a bit more about you mentioned as a direction to go in the polynomial algorithm but knots, and I was just wondering if you could say a bit more about what the connection would be.
I was not theory. Yes, so this knot recognition problem actually is a special case of something called sphere recognition. So right, so how does it work? So right, so if you have a knot in R3, you could also just put it into S3 by just putting the infinitely far point away. And now you could take the knot complement, which you get by thickening the knot slightly, and then taking that out, not just the knot, but kind of a slightly thickened knot. So that's kind of a 3-manifold and has a boundary, and the boundary is just a torus. Right, so you could take 2 copies of this 3-manifold and glue it together. How? Well, just take some isomorphism from the torus and glue it together onto this, and you get a 3-manifold. And the crazy fact is, you get the 3-sphere if and only if your knot is trivial. Because then you could untangle it somehow, these knots, and then you just take a torus and glue a torus onto a torus, and that's the 3-sphere. I mean, just think about, like, you have one torus like this, and then you have one torus going through the hole and kind of gluing it all up. But if it's kind of properly knotted, you get a different 3-manifold. And so this means this notch recognition is a special case of the sphere recognition problem. And then kind of there's this connection with Paraman and kind of these rotation system, which tells you that embedding a 2 complex in the 3 sphere is like identifying, it's kind of equivalent to this problem of checking whether a 3 sphere is isomorphic. Sorry, where the 3 manifold is isomorphic to the 3 sphere. Because I mean, if you kind of look the way how we always build the embeddings of 2 complexes into 3 sphere, first we embed these 2 complexes into some natural 3 manifolds that are built up from the 2 complex, and then we ask, is it isomorphic to 3 sphere or not? And this actually could kind of turn around a bit these arguments and then show that kind of this combinatorial embedding problem, embedding a 2 complex into 3 sphere is equivalent to checking whether a 3 manifold is isomorphic to 3 sphere.
So it's pretty exciting.
So maybe I'll stop the recording and we can continue with some informal discussion.